Hi everyone, my name is Philip Wisniewski. I'm a rising sophomore here at Purdue University studying computer science as part of the ANVIL REU program here at Purdue, and my project is AI-powered operational data analytics, predicting job queue times on ANVIL, funded by the NSF award number 2005632. Before we get into the project, let's just give a bit of a background on what ANVIL actually is. For those of you that don't know, ANVIL is the name of one of the supercomputers here on campus at Purdue. In fact, it's actually the largest supercomputer we have. It is funded by a $10 million grant by the NSF and used for a wide variety of disciplines all across the world and nation. Just a bit of a technical background to give you an idea of how big it truly is. There are over 1,000 different nodes, 1,000 compute nodes, which each have 128 CPUs. And for reference, I would guess that your computer, which you probably has somewhere between 4 and 16 CPUs. And so you can just see how large ANVIL truly is. It's like if 1,000 or 4,000 of your computers were all combined together. And so getting back into the actual project itself and just the motivation behind it. So I'll give you another example. Pretend that you're a research scientist wanting to use the supercomputer ANVIL, and you decide to code up your job, which is what the task you wanted to run is called, and you submit it to run. Then you have to wait in order for it to run. However, it can actually take a wide variety of times for your job to start running, depending on a variety of things, such as the state of the supercomputer at the time, as well as how many resources you request. This is where our project comes into play. We'll be developing a command line tool to be able to predict the start time of jobs based on a variety of input features and made this using a machine learning model. While there are currently some rudimentary queue time estimation methods, they're generally not very good, to say the least, and so we hope to be able to expand on this to provide not only an accurate, but primarily a useful model for users. Just giving a bit of the methodology used. We start by taking historical data from ANVIL, using the Slurm workload manager. That is the thing that stores essentially every piece of data on ANVIL supercomputer, and this contains about 4 million jobs ranging all the way back to 2021. So we take these jobs and the features associated with them, which can include things such as the amount of CPUs requested, the amount of time requested, as well as the start time and all sorts of other things like that. And we're going to use these to create additional features. The primary example of this is being able to replicate the state of the queue for the start time at any individual time. And so this can include features like how many CPUs are being used by ANVIL at any given time for any given job, and this can give an idea of how essentially free the computer is and how soon your job will be to run. From there, we'll be using this information to train and test a neural network using the PyTorch library, and then developing it into a command line tool for users to be able to use on their jobs. Now, just for those of you that aren't familiar, a neural network can be thought of similar to an artificial brain, where it takes in inputs, say for example your touch or smell or sight, sends it through your head or the hidden layers, which can be thought of as a bunch of neurons firing and activating each other, and finally spitting out an answer, which in our case will be the amount of minutes in a delay between the start and stop time, or start times and submit times. As for the data, just looking at it at a glance, there are roughly 4 million historical jobs on ANVIL. The data has multiple features available to it, roughly 40 that we could use. That includes things such as the amount of CPUs requested, nodes requested, as well as the amount of time requested, and other features like that. The data is very imbalanced, positively skewed, which can be seen in these graphs, in particular when looking at the amount of time it actually takes for a job to start, which we refer to as queue time. 90% of jobs take less than 10 minutes to start. However, those other 10% can range from minutes all the way to months, and that is a major problem for users when they're trying to run things urgently. As for the models themselves, we're using two separate models, a classification and regression model. The classification will be used to predict whether a specific job is over or under 10 minutes, and from there we'll be using the regression model, which will spit out an estimate on the exact time that it predicts a model or predicts a job will start to run depending if the classifier predicted that it will be over 10 minutes. The reason for this is just due to the such discrepancy in ranges of jobs and their distribution. We are deciding to train the model on over under 10 minutes in order to essentially not give the regression model as hard of a time in learning and predicting the different effects. To do this, we'll be using the PyTorch Python neural network library. Our results showed that the neural network actually outperformed other types of machine learning models, especially those seen in other studies. For example, there has been a study at the University of Edinburgh in the UK, and they used a k-nearest neighbors regressor, which can be thought of as essentially these jobs look similar, so therefore they probably have a similar result. And our neural network actually greatly outperformed it, as can be seen in the graphs, getting a rough percentage error of about 60-70% depending on the time we run it. So in conclusion, we successfully implemented a neural network model to be able to predict the wait time for jobs submitted to ANVIL. However, we still see room for improvement for future research, most notably more feature engineering, which could unlock more details about the state of the cluster and jobs, resulting in improved performance for the model, as well as the issue that many jobs greatly over-request how much resources they actually need. An example of this is for the amount of time requested. We found that some users were actually requesting or wasting 99% of the time which they request, which would be like saying that if you need 100 hours to do your job and it actually only takes 1 hour to run, that's not helpful, especially in providing variance and noise for the model to make it harder to learn. In conclusion, I hope you learned something and thank you for your time. Thank you.